So before starting lecture, I would like to say a few words. So these are the GÖRAN GUSTAFSSON lectures in mathematics. And as you can hear, it's sponsored by the GÖRAN GUSTAFSSON Foundation. And this year's speakers is the 20th GÖRAN GUSTAFSSON lecture. We're very grateful for this strong support from the GÖRAN GUSTAFSSON family and foundation to invite all these world-leading mathematicians here to Stockholm. And this year, the GÖRAN GUSTAFSSON lectures are also combined with a small conference, the GÖRAN GUSTAFSSON Symposium at the Institute Mittag-Leffler. And we're also very grateful for the Institute to facilitate the organization of this event. And June will give 3 lectures, so the first here, and then the second and third at the Mittag-Leffler Institute. So let me now introduce this year's GÖRAN GUSTAFSSON lecturer, June Ha. He first studied astronomy and physics in South Korea, and during these studies he met the famous Japanese mathematician Hironaka and got interested in mathematics and did a master in mathematics. And then he went to the US for his PhD studies at University of Illinois, Urbana-Champaign and University of Michigan. And then he received the prestigious Clay Research Fellowship and held position at Princeton University, Institute of Advanced Studies, and Stanford University. And already during his PhD, he made a very important breakthrough in the Heron-Rota-Welch log concavity conjecture, which he also then settled fully a few years after his PhD, together with Karim Adebasito and Eric Katz. And for this, he received the New Horizons in Mathematics Prize in 2019. He was also an invited speaker in the International Congress of Mathematics in 2018. And last year, he received the Samsung Huan Prize in Science. And he's currently a professor at Princeton University, and he will now tell us about Lorentzian polynomials.
Thank you for the introduction. It's an honor and great pleasure to be with you here today. So thank you for having me and thank you for being here. So today I'm going to tell you in very broad strokes why certain people find certain things interesting. And I'll try to give you a detailed and practical instruction to how to be one of those people if you want to. And I'm going to try to achieve that by trying to tell you how to formulate conjectures of certain type. And once you have a conjecture of that kind, I'll also try to tell you how to upgrade your conjecture to even stronger conjectures with stronger implications. So I'll start by showing you a pattern that has been discovered during the past decade by several different independent groups of mathematicians working in completely different fields. So let's say X is our mathematical object. And let's say it has some notion of dimension. And let's say that X has dimension D. Sometimes, and this will be the cases of our interest for today, we can find or construct, depending on your point of view, from X some other object, let's call it A, determined by X, which is a collection of vector spaces. Let's say a graded vector space, and each piece will be written by a kx, and the pieces range from k equals 0 to the dimension D. And these will be vector spaces over the real numbers. And you can also find a K, let's say Kx, which is the convex cone of graded linear operators on A. And these linear operators will raise the degree by 1. So AK goes to AK plus 1. And there's a whole family of it. And the family forms a convex cone. And thirdly and lastly, you can find P, which will be a bilinear pairing on AX and takes a value in real numbers. And this will pair piece of degree K with its complementary degree. And these triple of objects will satisfy a collection of seemingly oddly particular properties. Let's start with what you would call the symmetry property, which says that the bilinear pairing P is symmetric. And also the linear operators that we are concerned right now are also symmetric for all xy in A and all L in K. Yeah, K to K plus 1. So A is some graded vector space. So without apologizing at this point for the lack of motivation or anything, let me just keep going. Yes? Yes. The second property that you want is that the pairing P is non-degenerate. And let's refer to this property as the Poincare duality property. And the third is what's often called as the Hard-Lefschetz property, which says that the linear map from AKX to AD minus KX obtained by repeatedly applying linear operator L D minus 2K times is an isomorphism for any K at most D half and any L in our convex cone K. And the last property you expect to have is the Hodge-Riemann relations, which says that the bilinear pairing on kth graded piece of A obtained by sending x comma y to minus 1 to the k of px to the L to the D minus 2k y. So that is a composition of Poincare pairing and the Hard-Lefschetz isomorphism is positive, definite on the kernel of L to the D minus 2K plus 1. So one more than that would give an isomorphism. So again, for any K at most D half and any L in K. So historically speaking, the first instance of this construction of A and K and P from a certain mathematical object X appeared in geometry, Kähler geometry to be particular, where you take A to be the cohomology of KK forms on your Kähler manifold, compact Kähler manifold K, and KX is the cone of Kähler forms, where the letter K came from, and P is the Poincare duality pairing defined on the cohomology of your Kähler manifold X. But since then, people have found more and more examples of construction of this kind. So here's the known list of examples of such construction. So the list is short, but its breadth and the depth of applications is most remarkable. So perhaps the most famous instance of this is the case when X is a projective variety. Say over a finite field FQ, where you can take your AX to be the ring of, let's say, smooth, where you can take your AX to be the ring of algebraic cycles, modulo homological equivalence relation. And you can take your K to be the ample cone of all possible projective embeddings of X, and P is given by the intersection pairing on this X. And then the such a triple A and K and P satisfies the Poincare duality, Hart-Lefschetz property, and the Hodge-Riemann relations is perhaps one of the most important or famous open questions in the field of algebraic geometry, known as the standard conjectures on algebraic cycles. Second case is the case when X is a convex polytope, where you can take A to be the so-called the combinatorial intersection cohomology of convex polytope. And then it was proven that with suitably natural definitions of K and P, it does satisfy Poincare duality, Hart-Lefschetz property, and the Hodge-Riemann relations. This was done by Carew. Third case is the case when X is an element of a Coxeter group. And in this case, you can define or attach to such an X, the so-called Sargel bimodule. And with, again, it was shown by Ben Elias and Jordi Williamson that such a triple A and K and P does satisfy, for reasons completely unrelated to the examples 1 and 2, that it satisfies Poincare duality, Hart-Lefschetz property, and Hodge-Riemann relations. And the last case I wish to mention is the case when X is a matroid. So one of the basic class of objects studied in combinatorics. And in this case, in fact, you can take several equally natural triples A and K and P associated to a single matroid, and each one of them does satisfy all the properties listed here, and each one of them have rather interesting consequences. So at this point, one natural question that we can ask ourselves would be this. So if you believe that this pattern, rather unlikely pattern, is indeed quite general, and if you have a mathematical object, maybe not one in this list, but if you believe that your object has sufficiently rich structure, and maybe it does also fall into potentially this pattern, then the question is that of guessing. So how do you come up, maybe, with the right definition of A, which is something like the cohomology of X, that simplifies the complexity of your original object X into some sort of an algebraic structure, and K and P, so that you can start attempting to prove the Poincare duality, Hart-Lefschetz property, and the Hodge-Riemann relations. So for that question, it may be useful to go back to these cases of known examples and how we ended up with those definitions of A and K and P in those different contexts. The story usually goes like this. So there are very prominent conjectures that looks completely unrelated to each other for each one of these objects. And in algebraic geometry, there was this vague conjectures on the number of solutions of polynomial system of equations over a finite field. Say, as you vary your finite field, and that vague conjectures predict that they fall into particular patterns. And Grothendieck observed that if you define A and K and P in the right way, and if you can show that it satisfies Poincare duality, Hart-Lefschetz property, and Hodge-Riemann relations, then it actually implies vague conjectures. And Deligne famously proved vague conjectures without proving the standard conjectures, generating a few interesting stories. And there's a similar but more straightforward stories for each one of the objects follows. So for convex polytope, there was a McMullen's generalized lower bound conjecture. Which was a very specific prediction on the possible number of faces of various dimensions of a simplicial convex polytope. And Stanley realized that the three properties for a suitable A and K and P does imply the generalized lower bound conjecture. And for Coxer groups, Hassan and Lustig formulated a rather general conjecture on the so-called non-negativity of the coefficients of the Kazan-Lustig polynomial associated to arbitrary interval in the blue-hot poset of a Coxer group. And it is implied by the validity of Poincare duality Hart-Lefschetz property of the so-called Sorgel bimodule. And in the case of matroid, the validity of this listed properties implies various conjectures, Rota's and Brilovsky's, and Dowling, Wilson, and so on. And in each one of these cases, a detailed study of these conjectures led to the correct guess of A and K and P to be chosen for the relevant mathematical objects X. So far, so the story is that step one is you have to come up with very, very good conjectures that corresponds to the right-hand column. And once you have that, and you have to sit down and meditate for, I think on average for about a decade, to arrive at the correct definition of A and K and P. And once you have done that and arrive at the correct guess, aesthetically pleasing and logically fitting guess, and then again, on average, you have to sit down for another decade to actually prove that your guess satisfy all these properties, Hart-Lefschetz and Hodge-Riemann and Poincare duality. So clearly, the most difficult step of this process is the first one, because the latter two steps only took you, assuming for very best of us, it only took us like a decade. But to come up with these conjectures, it took our species like thousands of years. So what I want to sell today is perhaps a little bypass or a cheap alternative to these great conjectures that can be used maybe not to guess the precise form of AKP, but to at least convince us ourselves that there must be A and K and P that satisfy this. Because this is usually one of the biggest obstacles to start thinking about A and K and P. If you don't believe that they exist, you don't have motivation to think about them. And when you not have that, you will likely go nowhere. So let's say, let me introduce a piece of notation. So let's say the degree 0 piece is spanned by a single element. So it's one-dimensional. This is usually the case. Let's just give element a name, a spanning element A name. So let's just call it 1. And for linear operators, let's say Li. Let's define the degree of product of Li, say 1 from D, by the formula P of 1 paired with that composition of D linear operators applied to this chosen element 1. So you can see your choice of 1 really doesn't matter up to a constant. So to summarize, I have told you a formula how to convert a choice of D linear operators into a real number. So the right-hand side is a real number. And using this notation, you can prove of the following fact. So if you have n different linear operators, all in the closure of the convex cone K, so a limit of elements of K. And then if you look at this n variable polynomial, let's say with n variables, W1 to Wn, defined by some constant, 1 over d factorial, not important, multiplied to the degree of the linear combination, the variable linear combination of the Li's raised to the power of D. And this is a polynomial in W1 to Wn. So for every choice of real number Wi, you have a real number, and this function is a polynomial in W. And this polynomial is a Lorentzian polynomial. So this fact, which I just wrote down, doesn't mean anything to you right now because I have not told you yet what a Lorentzian polynomial is. But the key point here is that a polynomial being Lorentzian is a very testable property. So if you give me a polynomial in 5 variables of degree 10, then I can input into a computer and wait for a sufficiently long time, and then the computer will tell me whether it is or it is not a Lorentzian polynomial. And the proof of this fact relies on the validity of the Hodge-Riemann relations on A. So this testable property, so if you already have an interesting polynomial to look at, typically a generating function of some kind consisting of invariants that are extracted from your object of interest X, you can start looking at the question of whether this generating function being Lorentzian or not Lorentzian. And if it is, then you can start suspecting the existence of certain Hodge-Riemann relations behind your X, and that could be a starting point. So in fact, the definition of Lorentzian polynomial in one version of the story is constructed or reverse engineered to fit in this statement. So you look at the Hodge-Riemann relations, especially in degree 1, and you try to understand what kind of polynomial, what class of polynomials you would get if you look at the degree polynomials constructed in this way. And you try to come up with the most general class of polynomials that are satisfied by this degree polynomials constructed from Hodge-Riemann structures satisfying Hodge-Riemann relations, and then you end up with a definition of the Lorentzian polynomial, which I'll present to you shortly. But before doing that, let me give you 2 class of main examples of Lorentzian polynomials. So probably this is the most classical case where you start with n convex bodies in d-dimensional space. And you look at this function which computes the volume of linear combinations, variable linear combinations of the given convex body C1 to Cn. So this sum represents the Minkowski sum of convex bodies, and the volume here simply refers to the Euclidean volume of a convex body. So this expression becomes a function of W, which is in fact a polynomial in W, and this is a Lorentzian polynomial. And that statement implies the classical Alexandrov-Fenchel inequality, which is one of the backbones of the convex analysis, the field of convex analysis. And if you look at actually the proof of the Alexandrov-Fenchel inequality from the right generality, in fact, what is actually proved is the stronger statement that the volume polynomial here is Lorentzian. And the Alexandrov-Fenchel inequality on the so-called mixed volumes of convex bodies Ci, which are the coefficients of this polynomial, is deduced from that analytic property. The second example is from algebraic geometry, where you have n different Neff divisors on a d-dimensional projective variety. Over a field F. And here you compute the degree of the self-intersection of the linear combination of the DIs. So here, Neff refers to those classes of divisors that arise as limits of ample R divisors. And take linear combination of them. It's a Cartier divisor. You can take the self-intersect with itself, right number of times, and you end up with a number by counting the number of points. And such polynomials also turn out to be Lorentzian. And sometimes these polynomials are called similarly to the previous case, volume polynomial, but over this field F. In the special case when F is C and these divisors are ample, then the name makes sense because the resulting polynomial does indeed compute the volume of your projective manifold in that case, with respect to the associated metric. But the notion of Lorentzian polynomial is indeed more general than the cases covered by examples 1 and 2. So there are polynomials Lorentzian, but not arising from either the case 1 nor in the case 2. So now let me finally tell you what the Lorentzian polynomial is. So we're going to define a Lorentzian polynomial as a particular class of homogeneous polynomial in n variables. And we're going to define this class degree by degree, starting from degree 2. So the case of quadratic forms. And the first definition is that of L naught of 2n, and this little circle here is there to indicate that I'm now going to define an open subset of the space of all quadratic forms. So L naught 2 is the set of quadratic forms with positive coefficients and Lorentzian signature, which is single plus and all minus. So this is indeed an open condition. All the coefficient positive, that's open condition, and the signature viewed as a quadratic form having exactly one positive and all the negative eigenvalues is also an open condition. And for higher D, definition is that L naught Dn consists of homogeneous polynomials of degree D in n variables with the property that if you take the ith partial derivative of f, then it belongs to L naught D minus 1 to Dn for every variable I. And finally, the closure of L naught Dn is declared to be the set of Lorentzian polynomials. So the important condition here is that a positivity here, which in the context of the previous discussion comes from Hodge-Riemann relation in degree 0, and that of having Lorentzian signature, which comes from the Hodge-Riemann relation in the next degree, which is degree 1. And you want to construct a class that is closed on the partial derivatives. And this is the most efficient way of doing it. So a Lorentzian polynomial is defined as the limit of polynomials in L not Dn, which you may choose to call the strictly Lorentzian polynomials. So given this definition, you can ask, is there a way to decide whether a given polynomial is Lorentzian or not? And this answer to this question is the main point of this lecture and what was advertised briefly before. So just by looking at the definition, this is completely not obvious. So if I give you a very concrete polynomial, let's say, let me give you a few of them. Maybe something in 2 variables in degree 3, sum of 2 cubes, or maybe something like this, or maybe something like this, and so on. And if I ask you which of them are Lorentzian and which of them are not Lorentzian, the definition does not tell you what you should do. If you want to show that something is Lorentzian, you have to be, in principle, explicitly produce a limiting sequence of polynomials, each one of which belongs to L not Dn, which limits to that one. And this choice is not obvious. And if you want to show that some of these polynomials are not Lorentzian, then you have to find the reason why it cannot be approximated by such a sequence in L not Dn. So the answer turns out to be this one is not Lorentzian, this one is not Lorentzian, and this one is Lorentzian. And we'll soon see why that is so. So miraculously, the answer to the stated question is yes. And let me tell you how to decide it. So for that, let me define a few more symbols in parallel to this definition here. So L2n, I'll again work with homogeneous polynomials in n variables and work by degree, starting from the case of degree 2. And L2n, let's define it to the space of quadratic forms with non-negative coefficients, with at most one positive eigenvalue. So this is a closed subset of the space of all quadratic forms because I have a one closed condition, non-negativity, and at most one positive eigenvalue condition, again, a closed condition. And for larger D, LDN, let's define it as the space of all homogeneous polynomials of degree D in n variables with a property that its ith partial derivative belongs to LD minus 1 to the n for all I. And this is the important part, the monomials appearing in F are the set of lattice points of an integral generalized permutohedron. So the keyword here is the integral generalized permutohedron. So this is a class of convex polytopes living in Rn that is defined by the simple condition of having all edge directions having the form EI minus EJ for some I and J, where EI is the ith standard unit vector in Rn. So all the edge directions should be one of the root directions of root system of type A. And the theorem with Peter-Branden here is that LDN is the space of Lorentzian polynomials. So to show that left-hand side is contained in the right-hand side, you must show that so long as your monomials form the lattice points of a integral generalized permutohedron, you have to show that they can be approximated by strictly Lorentzian polynomials. And to show the other inclusion, you have to show that whenever you have a converging sequence of strictly Lorentzian polynomials, in the limit, the monomials that can appear always should form an integral, the lattice points of an integral generalized permutohedron. And the point here is that checking whether something is in here is a testable property. So if you give me a polynomial, I just look at all the monomials and maybe take the convex hull and just look at all the edge directions of the convex hull, so called the Newton polytope, and whether all the edge directions are in the right direction, EI minus EJ. And you have to make sure that you're not missing any lattice points of that integral generalized lattice. So going back to this example, so maybe I have for cubic in 3 variables, I have these 10 possible monomials. And for the first one, I have this monomial here, a cube, and I have another cube. And that is not good, because if I take the convex hull, then I'm missing the middle 2 points. So it cannot be in L3, 3. So this one is not Lorentzian. This one, I have a 1 monomial here. I have another monomial here. I take the convex hull. So I'm not missing any lattice points in between. But the edge direction, and there is only one edge, is in the wrong direction. It's not EI minus EJ. So that cannot be Lorentzian. So this one does have a good support. So it has only 1 point. So a zero-dimensional generalized permutohedron with no edges. And it turns out to have the right signature condition. So the process of convincing yourself of the existence of A and K and P that was mentioned in the beginning looks something like this. Maybe you have your favorite mathematical object X, and maybe you have your favorite way of extracting numbers out of it, maybe a whole family of numbers that can be put into a generating function. So that maybe you have a polynomial or family of polynomials associated to your X. And then what do? you immediately check whether the monomials that appear or the possibilities of non-vanishing invariance form the lattice points of a generalized permutohedron. And if that checks out, you immediately check the signature condition, or in other words, you check whether your generating function is a Lorentzian polynomial. And if that test pass, then I would say that you have a good chance of looking at an object that hides the triple A and K and P that in the behind of it. So let me show you one or two cases of generating conjectures in this way. One thing that becomes apparent with enough experience is that it's extremely useful to have a name for the so-called this normalization operator, which sends a polynomial C alpha to the W alpha to C alpha W to the alpha divided by alpha factorial. In other words, I'm going to transform all the generating functions to the exponential generating functions. Somehow in this context of Lorentzian polynomials, the exponential generating function is the right generating function to look at. Roughly speaking, the generating functions you should use when you're dealing with cohomological objects, and the exponential generating functions, you should use these guys when you're dealing with homological objects. And in this case, we are looking something like the volume polynomial over F, say, defined for any fixed list of divisors. And whenever you have a cycle, you can pair it and come up with a volume polynomial. So this is the right thing to look at. So one of the things you can prove for one of the most famous generating function in algebraic combinatorics is that for any partition lambda, the normalized Schur polynomial which is the exponential generating function for the dimensions of the weight spaces of irreducible representations, finite dimensional of GLN, is that one is Lorentzian. So in symbols, if you look at the exponential generating function for the so-called Kostka coefficients, that's Lorentzian. Thank you for asking that. The question was, what is HMMS? So M here is Jacob Mathern, and this M is Carola Mazzaros, and this S is Avery Saint-Dizier. So in particular, you can do the same thing you would do to deduce Alexander-Fenchel inequality from the Lorentzianness of rolling polynomials to deduce the rather non-trivial algebraic fact that whenever you look at an irreducible representation of GLN and look at its weight diagram and choose any root direction, EI minus DJ, and just walk along the weight lattice and just record the weight multiplicities that you encounter along the way, then the sequence you get should be always log concave. So this is one algebraic statement that is currently not understandable purely within algebraic framework of representation theory of GLN. It's a special case of a conjecture proposed by Andrei Okounkov in the early 2000s. And motivated by this result, we have looked at some other similar generating functions in algebraic combinatorics and came up with the following conjecture. The normalizations of the following polynomial are Lorentzian. So one, the Schubert polynomial for any permutation. Two, skew-Schur polynomial for any skew partition. Three, Schur P polynomial for any strict partition. Or the key polynomial for any composition. And five, homogenized Grothendieck polynomial for any permutation. The exact nature of each one of these polynomials is perhaps not important for the purpose of this talk. And maybe the fact that their definition not being important is important. So I barely remember the definitions of these combinatorially defined polynomials. And yet, we were able to suspect that these statements might be true and came up with these conjectures. So what do we do? When you have at least some indicating evidence for this sort of possibilities, and whenever some maybe combinatorialists hand you an interesting generating function, what do? You immediately check whether its Newton polytope is a generalized permutohedron. And this can be done by computer. And once that was done, perhaps you refine your computer search a little bit more and check whether actually their normalizations are Lorentzian. And if that checks out, in fact, you don't have to stop at this point. So in the very like a universally combinatorial setting such as this one, you can even go further and make the existence conjecture, such as the one saying that there must be a projective variety equipped with n different polarizations, say in F divisors, whose volume polynomial produces a Schubert polynomial, for example, or Schur P polynomial. So in whatever context, whenever you see a natural generating function that appears to have a Lorentzian property, if you're an algebraic geometer and if you like geometry, you can interpret as strong evidence for a natural but yet unknown projective variety waiting to be studied further that explains the Lorentzian property of each one of these polynomials.
The ones in this by partitions or in this by permutation?
Yeah, so I mean the ones indexed by permutations. And I should a little bit, so 1, 2, 3, 4, these are like by definition, these are homogeneous polynomials. Grothendieck polynomial, it comes from the study of K-theory of Schubert varieties, and they are inhomogeneous and they have a coefficient that are alternating in sign. So when I say homogenized Grothendieck polynomial, I mean the one you have by introducing extra variable to homogenize the whole thing and fix the sign in alternating degree to make all the coefficients non-negative. Okay, so there are a few Lorentzianness and the corresponding existence type conjectures that you can formulate. But I hope that there will be more of these conjectures coming. And compared to the standard conjecture type statements that are both hard to prove, but even more importantly, that are hard to formulate, these Lorentzian style conjectures are much more accessible, and it's a fun direction to look at as a group in the future. So let me stop my talk here. Thank you.
So thank you for this very wonderful lecture. So are there any questions in the audience?
Just a short question to start with. It's known that Lorentz polynomials come from the beginning from Minkowski space and special relativity, 1s and a. And the wave equation with one time we understand perfectly. But if you have two plus signs in your signature, then the wave equation gets very messy in general. Is it the same if you have two signs, two minus?
I suspect so if you start with another signature, then the corresponding combinatorial condition that may appear replacing this condition, I think it will be not very well structured, as in the Lorentzian case. So the Lorentzian signature is very special among all signatures to make this neat theory work.
Yeah, so thank you for the talk. So I have a question about log concave sequences. So can you mention, where these, so in your talk you haven't mentioned, let's say if I have a sequence A0 to AN, where do these sequences live in AN and K?
So in a sense, log concave sequences, you can think of it as a theory of Lorentzian polynomials in two variables. So whenever you have a homogeneous polynomial in two variables, you can order its coefficients according to the natural order they appear. And this bivariate degree D homogeneous polynomial is Lorentzian exactly when the normalized coefficients, so the sequence you obtain, is log concave and has no internal zeros. So the no internal zero condition corresponds to having all the lattice points in an integral generalized permutation. And the signature condition, the eigenvalue condition, corresponds to the log concavity inequality. So this is a typical log concavity inequality. So you can get this inequality from the Lorentzianness of the original polynomial, perhaps by specializing some variables equal to each other.
Thank you for your talk. So one question: the lattice points of a generalized permutohedron are an example of valuative invariance of a polytope. Does this come into play when we study Lorentzian polynomial at all? Does this simplify some of the things you need to check to study them?
Let me try to say what I think is somewhat relevant to your question. Is that you can develop the theory of Lorentzian polynomials not just over the real numbers, but over other ordered fields, perhaps with evaluation. And the theory works more or less the same way. But here, this lattice points of an integral generalized permutohedron is what is known as the convex set in discrete convex analysis. And there is also, they have a notion of discrete convex functions in discrete convex analysis. And if you work over the valued over ordered field, and if you interpret the evaluations of the coefficients as a discrete function defined on the Newton polytope, then the convexity of that discrete convex function corresponds to the Lorentzianness of its generating function. So I would say it's not unrelated.
Thank you for the talk. I have two questions. The first one is, since the property of being Lorentzian shows up very clearly looking at the coefficients, you can conclude something about the evaluations of the polynomials. There is a sort of convexity or concavity property that you can read off from the evaluations.
Yes.
That's the first part. And the second part is somewhat related, but do you expect that an analog theory of Lorentzian polynomials could exist for log convexity of sequences? Because it happens sometimes that once one deals with sequences that respect the other inequality. So yeah, that's two questions.
Yeah, so for the first question, which concerns the analytic properties of the Lorentzian polynomial viewed as a continuous function, there is a nice answer. So whenever you have a Lorentzian polynomial f in n variables, which you can view it as a function on Rn to Rr, and if you can restrict your function to the non-negative orthant or positive orthant, and then you can prove that log of f is concave. So the property of being Lorentzian is closed under taking partial derivatives. So you can actually show that log of any partial derivative of f is concave on the non-negative orthant, or is identically zero. And it turns out that this necessary condition is also sufficient for the Lorentzianness. So there is a, you could say, like a purely analytic or continuous characterization of being Lorentzian. And the second, there was a second question of trying to develop something analogous theory, replacing log concavity with log convexity. My guess is that the answer would be yes, but I do not know the exact shape of this theory, but I agree to your intuition that there are many, many evidence pointing to the existence of such a nice theory. But let me try not to say more to avoid saying something stupid.
So can you add the Stanley symmetric functions to your list of conjectures, maybe?
I don't know, but
I think that's most likely true. I have another question also.
okay.
Have you an example where you don't have to normalize the symmetric functions?
That's right. That's another also very interesting question, and again the answer is yes. So another typical conjecture or theorems that I have in mind, in addition to the sure polynomial result, is the basis generating polynomial of a matroid. But this is a special case of a more general polynomial which you can construct in matroid theory. So you can define the basis generating polynomial for a morphism of matroid, which always turns out to be Lorentzian without normalization. So a special case of this is the generating polynomial for the independent sets of a matroid, which is Lorentzian without normalization. So you need to homogenize, but you don't have to normalize. So this is the reason why if you count the number of independent subsets of, say, a vector configuration, then the resulting sequence is always ultra log concave and not just log concave. So this difference amounts to, yeah, but in order to just add one more thing, this no need to normalize a basis generating polynomial is often an indication of like a very interesting phenomenon. So for example, it's completely unclear in those cases whether they come from the volume polynomial of projective varieties over F. So if you go further, push your conjecture and make it into existence conjecture of a certain projective variety kept with several polarization, it typically becomes a very interesting or difficult question. So in particular, we don't know the answer to the independent set generating polynomial, whether it does come or does not come from a projective variety, even when your matroid is realizable over a field.
I have a quite general question. Like, AlphaGo has already beat the world's best Go gamer. So do you think maybe one day computer can beat mathematician?
I couldn't hear very well. Can you repeat the question?
The computer program AlphaGo has already win over the best Go gamer in the world.
Yeah.
So do you think maybe one day there is a computer program that can win over all the mathematicians?
Well, I don't know, but there was some recent results. I heard some stories that one of the characters that I briefly mentioned, Jordi Williamson, who figured out the Hartleb-Schatzbrenker duality and Hodge-Riemann relations, work with that exact same team, like the DeepMind team. And they have claimed to collaborate successfully between computers and humans to come up with interesting conjectures that they would not have came up. So we'll see.
Thank you.
Yeah.
Any further questions in the room? Also, if you on Zoom want to ask a question, raise your hand. I'll try to let you speak.
So one more question from my end. I want to ask, you have a generating polynomial and you are checking whether it's a Lorentzian polynomial or not. What if you begin with a multivariate generating function with, so it's a power series, not a polynomial. Then, I mean, do you have some analogous theory?
I strongly suspect that there is, and I do have like my favorite example in mind. So this is all about this sure polynomial thing is all about like irreducible representation of GLN of finite dimension. So in general, if you have some Lie algebra, maybe SL and C, and there is one irreducible representation for every weight lambda, integral weight lambda, and when that lambda is dominant, the resulting thing is finite dimensional. But without that, there is this highest weight theory, which produces irreducible module, possibly of infinite dimension, associated to every choice of the weight. And in general, the weight multiplicity generating function will be a power series. And we conjecture that in general, those power series will be Lorentzian in the following sense. So now this, you can think of this is an array of coefficient as some discrete function defined. And the point is that you can shift the domain of this discrete function in parallel without changing the Lorentzian property, at least for polynomials. So the possible definition of Lorentzian polynomials for power series in that setup would be to shift so multiply by a sufficiently positive monomial so that all the coefficients get shifted by a positive amount, and just intersect it with the non-negative orthant. And throw away every coefficient that does not lie in the non-negative orthant, so that you end up with a homogeneous polynomial. So this is a finite part. And the condition is that that finite part should be Lorentzian. But of course, you can cover as much coefficient as you want by shifting it by further and further positive amount, and all of them should be Lorentzian. And the conjecture in that particular irreducible representation setup is that the generating function for the weight multiplicities of highest weight modules are all Lorentzian.
So you've outlined Lorentzian polynomials as a conjecture-making machines, what is key, etc., right? What about proving the tough stuff, for instance, growth in the standard conjectures? Do you think the approach gives some insights how to... there we know what the
I'm sure that it will be absolutely useless. because Lorentzian polynomials are very good in that they are easy objects. So the objects are easy. It's easy to check whether something's Lorentzian or not. But growth-ending standard conjecture thing, even if you have maybe you don't want to prove it for all projective varieties, but if you have, somebody gives you one projective variety, and if you want to check whether standard conjectures are true for that one projective variety, and if you have access to all the supercomputers in the world, then you know what you should do, but still it's impossibly hard. So there is an enormous difference in the complexity of the questions that you can ask.
So the Lorentzian polynomials may be or studied to understand maybe the Riemann relations in dimension 1.
Right.
But could there be some gadget that you could study for higher Hodge Riemann relations, and could that maybe because we know that there are Lorentzian polynomials that do not come from projective varieties.
That's right.
But if you add more higher up,
I do not want to be pessimistic, but this is related to the previous question on the specialness of the Lorentzian signature. If you go and look at the higher Hodge-Riemann relations, then you no longer have Lorentzian signature. So it's completely unclear whether we will have a nice interaction with combinatorics that we have seen in this case. At least, we do not have a clear idea at the moment, what the theory would look like.
But could there be some Lorentzian gadget that you could study?
Maybe, but we have no idea at the moment.
Let me check if there's some. So we have a question from Tao Gui. Let's see if this works. I'm going to do the following. Now, if you ask something to work. Yeah. We have to give up. So, and now I'm also beautiful, unfortunately. So, I think we have to simply end here. But it's a pleasure to have you here. To give this wonderful talk. And the symposium will continue this afternoon at Institut Leffler. And yes, let's thank you.